Let we begin our session with binary adders. These binary adders are the examples of arithmetic and logical circuits of combinational circuit. Arithmetic circuits examples are adders, subtractors, multipliers and dividers. So in adder circuit, the basic adder is a half adder. So it is a basic building block for performing the addition of two single bit numbers. Half adder is a combinational logical circuit with two inputs and two outputs. The half adder circuit designed with two single bit binary numbers which are designated with A and B and produces two outputs as a carry and a sum. So now I'm going to give the block diagram of your half adder circuit where it accepts the two inputs which are symbolized with A and B. So it will add two single bits. So hence we have two inputs which are labeled with AB and produces two outputs which are sum and carry output. So now upon drawing that block diagram, next we need to draw the truth table. So with the possible input combinations of two inputs, so AB we have four combinations 0 0, 0 1, 1 0, 1 1 and the derived outputs from a half adder is sum and carry. So we represented that as a outputs sum and carry. So it's a single bit adder. So now bit by bit we are going to add. So here 0 plus 0 would generate the sum bit is 0, carry output is 0. 0 plus 1 summation output is 1, carry output is 0. 1 plus 0 is a simple adder. So single bit adder. So 1 plus 0 will give you the summation 1 and a carry output of 0. 1 plus 1 is 1 0 is the actual output. In that 1 0, so 0 is the least significant bit which is considered as a sum bit and 1 is the most significant bit which is considered as a carry output. So now this is your basic logical diagram using an exclusive OR gate and an AND gate. So with this we are going to draw the logical diagram of your half adder using one exclusive OR and one AND gate. Now how to derive these output expressions is using your K-map method. So now from the truth table, so if I write your standard SOP expression for each output, summation output will give you sigma m of 1 comma 2, carry output will give you summation of 3. So since our functional value for that combinations are logical one and hence we represented that in your output expression as in the form of your SSOP. So sigma m of 1 comma 2 is equal to A exclusive OR of B that is equal to A bar B plus AB bar where carry is only one minterm is available and a two variable K-map so which will give you AB. So now we mapped your function of carry along with your summation using your two variable K-map. My inputs I have represented as your input variables of K-map and now we're going to map your functional values of your carry and your summation functional value. So as here, so these minterms are diagonally arranged, so we can't pair it. So hence we need to write or we need to consider these as a isolated minterms. So now those isolated minterms to be written as it is in your summation expression as here A is 0 and B value is 1, hence AB bar. So A bar B. So whereas here A value is 1 and B value is a 0, hence this isolated minterm is written as AB bar. So AB bar plus A bar B is your final minimal expression of your summation function which represents the Boolean expression of your A exclusive OR of B. Next, for a carry output, so we map your function, only it is having one minterm which is on tree. So now if it doesn't have your any pair formation, then it is also considered as a isolated minterm, and that isolated minterm is written as, since A is 1 and B is also 1, so it is the product term is written as a carry. Output minimum expression is equal to AB. So now using one simple exclusive OR gate and one AND gate, we can implement the logical diagram of your half adder circuit. So upon transferring the inputs of AB to the inputs of your exclusive OR gate, output of your exclusive OR will implement the summation function, which is equal to A exclusive OR of B, and carry output is implemented by using a logic gate, which is called as AND gate, is equal to A and B. So carry output is equal to A and B. So like this we design your half adder circuit. Now, so here we have not mentioned any carry input. So hence, in order to avoid that drawback, we are going to prefer the full adder circuit. Now these full adder circuits are developed to overcome the drawback of your half adder circuit. Now it can add two 1-bit numbers of A and B along with the carry input. So full adder is having now 3 inputs and 2 outputs in this combinational circuit. Hence we represented those 3 inputs as A, B as well as your carry input are the inputs of your full adder, and the outputs of this full adder is summation, which is represented with S letter, and carry output, which is represented with a C naught. So now let me design this full adder circuit using its truth table. Now this truth table of your full adder will have the possible inputs and outputs. So 3 possible inputs and 2 outputs. So if I have 3 possible inputs, total combinations available is here is 8. So now along with A, B, we also have your C input. Hence we have total 8 input combination, and we replaced all the inputs with the possible zeros and ones. Now it is also having 2 outputs, which are summation and carry output. Now in order to derive its output functional values of summation and carry output, let me add the bits bit by bit as a single bit addition. So 0 plus 0 is 0. So summation of A plus B, we are going to add your C in. So now C in is also 0. Summation is equal to 0. No carry generated from this addition. So carry output is 0. So next combination is 0, 0, 1. So 0 plus 0 is 0. 0 plus 1 is summation bit is 1. Carry output is 1. Next 0 plus 1 is 1. Is the summation of A plus B, and to that summation of A plus B add C in, which is 0. So 1 plus 0 is 1, carry output is 0. Next 0 plus 1 is 1, 1 plus 1 is 2. So here 2 is equivalent to 1 0 in our binary. So least significant bit is considered as a summation bit, and the most significant bit is considered as a carry output. So now this carry output, now it is 1, where the summation bit is 0 for the combination of 0 1 1. Next 1 0 0 is your input combination. So 1 plus 0 is 1, 1 plus 0 is 1. So summation is 1, carry output is 1. Next 1 plus 0 is 1, 1 plus 1 is 2, where 2 is 1 0. So we consider carry output of full adder is 1, and with the summation bit is 0. Next 1 plus 1 is 2. 2 plus 0 is 0. So 2 plus 0 is 2. So here 2 is written as carry output is 1, with the summation bit is 0. Next 1 plus 1 is 2. 2 plus 1 is 3. Where 3 in binary is 1 1. So 1 we considered as a carry output, and the least significant bit of summation is also equal to 1. So now upon deriving your truth table, then we have to minimize your function using your K-map method. So now let me write your each logical expression of your output summation, where you have your functional value is 1. So that corresponding minterms we need to write inside the parenthesis of your standard SOP function. So summation is equal to sigma m of, so for the decimal code of 001 it is 1. So next the decimal code of 2, it is 1. So hence we mentioned the minterm 2. Next, for the minterm 4 also the functional value is 1, and for the minterm 7 the functional value is 1. So hence summation output function, if you write it as standard SOP, which is equal to sigma m of 1 comma 2 comma 4 comma 7. The same manner, carry output functional value is 1 for 3 4 3 5 6 7. So carry output is equal to sigma m of 3 5 6 7. Now let me use the k-map method for minimizing. So it's a 3 variable function, hence we prefer the 3 variable k-map here, and upon mapping your summation and carry output, let me use the adjacent method for finding your minimal expression. Now as here in a summation function, all minterms are arranged diagonally. So now all are treated as your isolated minterms. So since it doesn't have here any pair combination. So when it doesn't have any pair combinations, so then all are treated as your, now we are going to treat all these as your isolated minterms. So now isolated minterms in our final expression to be written as your minterms of 1, which is equal to a bar b bar c in. Minterm 2 is written as a bar b c in bar. Minterm 4 is written as a b bar c in bar, and minterm 7 is written as a b c in. So now, so we wrote this all the minterm, isolated minterms as here output expression of summation. Now, so if I wanted to write in terms of exclusive OR, let me take your Cin as a common from your first and last minterm. So Cin is taken as common, then we obtain a bar b bar plus ab. Next, if I take Cin bar as common from second and third minterms, so here third product terms we have Cin bar is common, so a bar b plus ab. So a bar b plus ab is written as a exclusive OR of b, and this I can write it as here a bar b bar or of ab is equal to complement of your A exclusive OR of B. So it is in the form of here. So A bar B. So hence, so we can obtain A exclusive OR of B exclusive OR of C in is your output function of your summation. So summation of your full adder is equal to A exclusive OR of B exclusive OR of C in. Next, carry output upon mapping. So we can form here three pairs here. So now because of this 3 5 6 7, so now we mapped here 3 5 6 7, so it can form your three pairs. So each pair can eliminate one of your variable which is not common. So first pair will have your BC in, this pair is having BC in, and so this pair is having your A value is common along with your Cn is common, and this pair is having your value of A variable is common from your two minterms, and B is common. So upon adding these all the product terms, we obtain your minimal expression of your carry output as AB or of BC in or of AC in is your output expression of your full adder. Now if I am going to draw the logical diagram of your AOI logic diagram and or invert logical diagram. So summation, so using only AND gates, so because all are product terms here, a bar b a bar b bar c in, a bar b c in bar, a b bar c in bar, a b c in is your summation function. So hence we use your four AND gates with one OR gate that can implement your summation function. Next, output carry is addition of these three product terms a b or of b c in or of a c in, hence we use your three AND gates in addition with one OR gate. Now upon adding these all the outputs of your AND gates of three AND gates we can to the input of your OR gate, we are going to implement your carry output function of a full adder section. Next, implementation of full adder using half adders. So now this can be done with your using your So we can also implement your full adder using two half adder circuits. Now let me rewrite your expression of your output. So by taking C as common, AB or of A bar B bar. So now I can write it as A exclusive or of A exclusive or of C is a summation, and C out is equal to. So now let me take here A bar. C is common from your first two terms. So then we have A bar B plus A B bar, and from this AB if I take common, so then it will be C bar R of C. So as C bar R of C is equal to 1, so hence if I replace that C bar R of C is 1, then I have here the final output expression is A exclusive R of B and of C plus AB is here the other form of your C out. So in order to draw the logical diagram of full adder using two half adders, we are going to use this two output expressions of a summation and carry output. Summation is equal to A exclusive of B exclusive of C in, and C out is equal to A exclusive of B into C in plus AB. Now using two half adders, we can implement your full adder circuit. So first half adder is having the inputs AB are transferred as your first two inputs, generates the summation and carry output. The second half adder, one of the input is here. The output of your first half adder is acting like a one of the input, first input of your half adder, and the second input comes from your third input of your full adder, which is C in. Next, summation of your second half adder will give you the full adder summation. And now upon transferring the carry outputs of two half adders carries to a OR gate, that OR gate will generate your carry output. So now let me pass your first two inputs of AB to a first half adder. So generates the summation output A exclusive of B with a carry output of AB using a AND gate. Next, in order to obtain your summation of your full adder, we transfer the first half adder output as the first input, and second input is transferred from your third input of your full adder. Now it generates the summation output of your second half adder will generate the output of your summation of full adder, and it also gives you the carry output which is C in into A exclusive of B. So second half adder carry output is connected as one input of your OR gate, as well as the carry output of your first half adder is acting like a second input to the OR gate. So now the OR gate output would generate your actual carry output of your full adder, which is AB or a C in and of A exclusive or of B. So now in order to add an array of bits, so we are not going to prefer your full adder, since full adder is the one which can add only 3 bits. So in order to do that parallel addition, we have to follow here a parallel adder circuit. Now this parallel adder circuit is constructed using your full adders by cascading. So cascading means output of your previous stages are connected as your inputs to the next stages. So next here we are going to connect, we are going to have the number of full adder sessions which are added is n number of full adders. How we are connected is output of your first full adder is connected as acting like a carry input for the second full adder, and now each full adder outputs are considered as a summation output, and the last full adder, which is the nth stage full adder carry output, is considered as your carry output of your n-bit parallel adder. Now let me design a 4-bit parallel adder. So design the 4-bit parallel adder which can add your 4 bits of your each number. So we are going to cascade 4 number of full adders which are designated as full adder 1, 2, 3, 4, and their respective inputs are A1, B1 are the inputs along with the carry input. Initial carry is 0. So hence this full adder is having 3 inputs of A1, B1, C0, and the second full adder is having the inputs of A2, B2, C1, where this C1 is the output of your first full adder acting like a carry input to the second full adder. So like this, upon transferring your carry outputs of your previous stage as your carry input, we're going to use the cascading method and construct your 4-bit parallel adder. So now each full adder will give you the summation output S1, S2, S3, S4, and then each will also give you the carry output C1, C2, C3, C4. These are transferred as a carry input to the next full adder sections. So now the final carry output is collected from the last stage of the full adder, which is from fourth full adder. Upon doing these connections, now so it can add your 4 bits at a time on your two numbers. Now here, so let I explain this with an example 1011, which I'm going to add with a 1101. So now, so upon adding this 1011 with a 1101, so now A1 is 1, A2 is 1, A3 is 0, A4 is 1, B1 is 1, B2 is 0, B3 is 1, B4 is 1. Now here, so let we add so 1011 with your, so now here A1 become 1, A2 is 1, A3 is 0, A4 is 1, and now the second number is 1101. So hence here B4 is 1, B3 is 1, B2 is 0, B1 is 1, where C0 is 0. So now first full adder will add A1, B1, C0. As these two are 110, summation S1 is equal to 0, C1 is equal to 1. Now for the second full adder, the inputs are 101. So summation will give you 0 with a carry output of 1. Now third full adder is having the inputs of 0, 1, 1. So summation S3 is 0 with a carry output of here 1. Next, last full adder, fourth full adder is having the inputs of A4 1, B4 1, C3 is 1. So hence S4 is 1, C4 is also equal to 1. So like this, so this 4-bit parallel adder will add here each two numbers with which are 4 bits on your each number is represented, and your summation would generate your 5 bits. So the first 4 bits are considered as a summation bit, and this most significant bit is your C4 bit. So like this, so we are going to construct your a parallel adder circuit. In the next session, we're going to start your subtractor circuit